Just as your car has a speed limit, the cosmic speed limit is known as the speed of light. This is the absolute point something can go as fast. Thus, it won't come as a surprise to anyone that distance in space is calculated using the speed of light. Both science fiction as well as many space travel enthusiasts talk about how man could one day travel at the speed of light to reach distant solar systems and planet of our galaxy. But this raises questions about whether traveling at such a speed is even possible, or more importantly, if whether it's a good idea in the first place. So stick with the video till the end to know the complete details. Now let's begin. Consequences of traveling at the speed of light. To begin with, traveling at the speed of light causes your mass to expand indefinitely, causing you to slow down. The faster you move, the more mass you have, according to the theory of relativity put forth by Einstein. When you're driving down the freeway on Earth, the same principle applies. When you're driving around, you weigh a little more than when you're perfectly still. As a result, traditional travel at the speed of light is impossible. But assuming it's possible, what will the consequences be? First, we must consider time dilation, which is defined as an actual difference in elapsed time between two occurrences as assessed by observers moving relative to each other or at various distances from gravitational masses. This is why after 6 months in orbit, astronauts returning from the International Space Stations have traveled 0.007 seconds into the future. Now, they haven't actually time traveled to the future. They have simply aged slowly compared to everyone else on the planet. Let's look at Alpha Centauri as an example. Let's pretend you can instantly accelerate to 99.9% of the speed of light and then decelerate without dying yourself or wrecking your ship. Because Alpha Centauri is theoretically 4.5 light years away, traveling at 99.9 for 4 Earth years would take around 2 weeks. Everyone and everything on Earth would have aged 4 years, while you would have just aged 2 weeks. To visualize the dilation effect for this voyage, think of it in one of two ways. Either time on the ship is moving 110 times slower than normal, or you're traveling a distance 110 times shorter. It's the same thing in terms of space-time. Of course, transmission from that distance means that any signal you send would take 4 Earth time years to reach Earth, so it's more likely that you'd arrive in the system. Do some study for a year or so, and then go. You'll have been gone for 9 Earth years but 1.24 years as far as you're concerned. Why can't we travel at the speed of light? E = mc squared is Einstein's most known and cliched equation, in which E represents energy, m represents mass, and c represents the speed of light. Mass and energy, according to this equation, are the same physical entity that may be transformed into one another. Because of this equivalency, an object's mass will rise as its energy from motion increases. In other words, the faster an object moves, the higher its mass. Only when an object moves really swiftly do this become apparent. Its mass will only be 0.5% greater than normal if it travels at 10% the speed of light. If it travels at 90% the speed of light, however, its mass will double. The mass of an object increases dramatically as it approaches the speed of light. When an object tries to go at 186,000 miles per second, its mass and the energy required to propel it become infinite. The amount of energy required to approach the speed of light, even for extremely small entities like subatomic particles, provides a huge hurdle to the viability of near-light speed space travel for man-made spacecraft or even ones built by aliens if the laws of physics as we understand them apply to them. The Large Hadron Collider, the world's largest and most powerful particle accelerator, has accelerated protons within atoms as close to the speed of light as possible. The Hadron Collider's researchers can only accelerate electrons to 99.9999991% of the speed of light. However, even a little proton would need near infinite energy to reach the speed of light, and humans haven't exactly worked out what near infinite energy is. As a result, no ordinary object can travel faster than or even at the speed of light. Theoretical proposals. An American physicist has suggested a proposal for how faster-than-light travel can be achievable in a new research study. Eric Lenz, a researcher at the University of Göttingen in Germany, conducted the study. Lenz and his colleagues believe that in the future, travel to faraway stars and planets may be conceivable. However, this can only happen if spacecraft travel faster than the speed of light. In 1 second, light can travel 300,000 kilometers. According to Albert Einstein's famous theory of relativity, it's impossible to move faster than the speed of light. As a result, a recent study on the topic has focused on hypotheses that go beyond conventional explanations of the matter. To achieve faster-than-light travel, they propose hypothetical particles and states of matter with extraordinary physical properties. According to the report, this type of material is either unavailable or cannot be made in sufficient quantities. The new work emphasizes a feasible engineering solution rather than theoretical research. This study outlines a strategy for enabling speedy travel by constructing a network of solitons, which serve as the foundation for a powerful propulsion system. A soliton is a small wave that maintains its speed and shape while traveling with minimal energy loss. According to the research, such technology might allow for travel at any speed. The findings were just published in the journal Classical and Quantum Gravity. According to a new statement describing the procedure, the technology uses the very structure of space and time structured in a soliton to propose a solution to faster-than-light travel. According to some experts, such warp drive technology might be employed to drastically shorten travel time. This could pave the way for future travel to far-flung space objects. Faster-than-light travel, according to the researchers' plan, might lead to far interstellar travel within a human lifetime. According to Lenz, a lot of work will be required to make the idea a reality. To be useful, the amount of energy required would have to be reduced to that of modern nuclear power reactors. He also stated that a method for developing and speeding up the solitons must be devised. The research and development process, according to Lenz, is challenging but not impossible. Additional steps could be taken in the coming years, with a fully working version likely within the next 10 years, according to him. Can we travel at nearly as fast as the speed of light? Understanding how particles are accelerated is one of NASA's responsibilities. Studying superfast or relativistic particles can assist in defending missions exploring the solar system and going to the moon, as well as educate us more about our galaxy. A well-aimed near-light speed particle can trip onboard circuits, and too many of them at once could cause radiation problems for humans traveling to the moon or beyond. They can also help us understand how to accelerate a spacecraft in the future to speeds fast enough to explore the cosmos. Acceleration can happen in 3 different ways. The majority of the mechanisms that accelerate particles to relativistic speeds use electromagnetic fields, which are the same forces that keep magnets on your refrigerator in place. Electric and magnetic fields, like 2 sides of the same coin, work together to propel particles across the universe at relativistic speeds. In essence, charged particles are accelerated by electromagnetic fields because they sense a force in the field that pushes them along, similar to how gravity pulls at mass objects. Electromagnetic fields can accelerate particles to near-light speed under the correct circumstances. Electric fields are frequently used on a lower scale on Earth to accelerate particles in laboratories. Pulsed electromagnetic fields are used in particle accelerators like the Large Hadron Collider and Fermilab to accelerate charged particles up to 99.9999896% the speed of light. The particles can be smashed together at these speeds, resulting in massive energy collisions. This enables scientists to search for fundamental particles and learn about the cosmos in the fractions of a second following the Big Bang. The second method is to use magnetic fields, which may be found all across space, encircling Earth and spanning the entire solar system. They even guide charged particles spiraling around the fields as they move through space. When these magnetic fields collide with one another, they might tangle. The crossed lines explode and realign when the tension between them becomes too great. This is known as magnetic reconnection. The quick shift in a region's magnetic field produces electric fields, which force all the charged particles in the area to be propelled out at tremendous speeds. Magnetic reconnection, according to scientists, is one method that particles such as the solar wind are pushed to relativistic speeds. The magnetospheric multiscale spacecraft was created and designed by NASA to study all elements of magnetic reconnection. The mission flies around Earth using 4 similar spacecraft to observe magnetic reconnection in operation. The findings of the data analysis can aid scientists in their understanding of particle acceleration at relativistic speeds on Earth and throughout the universe. Finally, interactions with electromagnetic waves, known as wave-particle interactions, can accelerate particles. The fields of electromagnetic waves can be squeezed when they encounter. Similar to a ball bouncing between 2 merging walls, charged particles bouncing back and forth between the waves can generate energy. These kinds of interactions happen all the time in near-Earth orbit, and they are responsible for accelerating particles to speeds fast enough to harm electronics on spacecraft and satellites. The Van Allen probes and other NASA missions aid scientists in their understanding of wave-particle interactions. Some cosmic rays that originate outside our solar system are hypothesized to be accelerated by wave-particle interactions. A blast wave is propelled away from the star's center after a supernova explosion. It's a hot, compact shell of compressed gas. Wave-particle interactions in these bubbles, which are filled with magnetic fields and charged particles, can shoot high-energy cosmic rays at 99.6% the speed of light. Wave-particle interactions may possibly have a role in the acceleration of the sun's solar wind and cosmic rays. That's all for today, folks. We hope you found the video informative and fun to watch. Also, tell us in the comments section whether you think it's a good idea to travel at the speed of light. And if you enjoyed the video, hit the like button, subscribe to the channel, and hit the bell icon next to it for regular updates. Goodbye!